Welcome to our lesson on speed and velocity. Motion is everywhere around us, from the cars on the highway to the planets orbiting the sun. Understanding how things move is fundamental to physics. Every day, we observe objects in motion: a car driving down the street, a runner jogging in the park, or even a ball rolling across the floor. But how do we describe and measure this motion scientifically? To describe motion properly, we need two key concepts: speed and velocity. While these terms are often used interchangeably in everyday language, they have distinct meanings in physics. Speed tells us how fast an object is moving, while velocity tells us both how fast and in which direction. This distinction becomes crucial when analyzing motion in physics and engineering. Throughout this lesson, we'll explore how to calculate speed and velocity, interpret motion graphs, and apply these concepts to real-world situations. Understanding these fundamentals will give you the tools to analyze any type of motion. Motion is one of the most fundamental concepts in physics, and mastering speed and velocity will open the door to understanding more complex topics like acceleration, forces, and energy. Let's begin our journey into the world of motion. The key difference between speed and velocity lies in one crucial factor: direction. While these terms are often used interchangeably in everyday conversation, they have distinct meanings in physics. Speed is what we call a scalar quantity. This means it only tells us how fast something is moving, without any information about the direction of movement. Velocity, on the other hand, is a vector quantity. This means it includes both the speed and the direction of motion. A vector has both magnitude and direction. Here's a practical example that shows the difference clearly. A car traveling at 60 kilometers per hour has a speed of 60 kilometers per hour. But if we specify that the car is moving 60 kilometers per hour toward the east, we are describing its velocity. This distinction becomes important when objects change direction. Two cars traveling at the same speed but in different directions have different velocities, even though their speeds are identical. Distance time graphs are powerful visual tools that help us understand how objects move through space and time. These graphs provide a clear picture of motion by plotting the relationship between distance traveled and time elapsed. In a distance-time graph, we always place time on the horizontal x-axis and distance on the vertical y-axis. This standard setup allows us to see how distance changes as time progresses. Let's examine uniform motion first. When an object moves at constant speed, the distance-time graph shows a straight line. The steeper the line, the faster the object is moving. The slope or gradient of this straight line represents the speed of the object. A steeper slope means higher speed, while a gentler slope indicates lower speed. Now let's look at non-uniform motion. When an object's speed changes over time, the distance-time graph becomes curved rather than straight. In this curved graph, the object starts slowly and then speeds up. The curve gets steeper as time progresses, showing that the object is accelerating. Finally, when an object is stationary or not moving, the distance-time graph shows a horizontal line. The distance remains constant while time continues to pass. Let's see all three types of motion together to compare their different patterns on distance-time graphs. Remember these key points. Straight lines indicate uniform motion with constant speed, curved lines show non-uniform motion with changing speed, and horizontal lines represent stationary objects. The slope of any line tells us about the speed of the object. Distance-time graphs tell us a story about how objects move. By learning to read these graphs, we can understand different types of motion and calculate important quantities like speed and velocity. A straight line on a distance-time graph indicates that an object is moving at constant speed. The object covers equal distances in equal time intervals. The steepness of the line, called the slope, tells us how fast the object is moving. A steeper slope means higher speed, while a gentler slope means lower speed. A horizontal line on a distance-time graph indicates that the object is stationary. The distance remains constant over time, meaning the object is not moving. A curved line indicates that the object's speed is changing. This means the object is either accelerating, speeding up, or decelerating, slowing down. To find the instantaneous speed at any point on a curved line, we analyze the slope of the tangent line at that specific point. The steeper the tangent, the higher the instantaneous speed. Remember these key patterns. Straight lines mean constant speed, steeper slopes mean higher speeds, horizontal lines mean the object is stationary, and curved lines indicate changing speed with acceleration or deceleration. Now we'll work through practical examples to master calculating speed and velocity. These step-by-step problems will help you apply the formulas confidently. First, let's recall the speed formula. Speed equals distance divided by time. We can visualize this relationship using a formula triangle. Now let's substitute our values. Distance equals 10 meters and time equals 2 seconds. Speed equals 10 meters divided by 2 seconds, which gives us 5 meters per second. Now let's examine a more complex example involving velocity. Remember, velocity considers both speed and direction and uses displacement instead of total distance. This problem illustrates the key difference between distance and displacement. Let's visualize this with a diagram showing the man's journey. Let's analyze this step by step. The man walks 50 meters east, then 50 meters west, ending up at his starting position. His total displacement is 0, even though he traveled 100 meters total distance. Let's work through one more example using the average speed formula. This will help you understand compound measures and unit conversions. First, we need to convert the time to the same units. 1 hour 30 minutes equals 1.5 hours. Then we apply the average speed formula. Finally, let's examine a more advanced problem involving acceleration and multiple motion quantities. This shows how speed and velocity calculations apply in complex scenarios. This problem asks us to find average velocity when we know initial velocity, final velocity, and time. The average velocity is simply the sum of initial and final velocities divided by 2. These examples demonstrate the key principles. Speed uses total distance, velocity uses displacement and direction, and always pay attention to units and time conversions. Practice with similar problems will build your confidence in motion calculations. Understanding speed and velocity extends far beyond the classroom. These fundamental concepts are essential in countless real-world applications that impact our daily lives. In transportation, GPS systems use velocity calculations to provide accurate navigation and arrival times. Traffic engineers analyze speed patterns to optimize road design and reduce congestion. Sports science relies heavily on speed and velocity measurements. Athletes use this data to improve performance, while coaches analyze movement patterns to optimize training programs. In physics research, particle accelerators require precise velocity control to study fundamental particles. Astronomers calculate celestial object velocities to understand cosmic phenomena. Engineers design safety systems like airbags and collision avoidance systems using speed and velocity calculations. Robotics engineers program precise movement control for automated systems. Now let's review the key concepts we've learned about speed and velocity to reinforce your understanding. The fundamental difference between speed and velocity is that speed measures how fast you're moving, while velocity measures how fast you're moving in a specific direction. Distance-time graphs are powerful tools for visualizing motion. The gradient or slope of these graphs directly represents speed. These concepts form the foundation for advanced physics topics. Understanding displacement, velocity, and their relationships prepares you for studying acceleration, momentum, and forces. To master these concepts, practice plotting and interpreting distance-time graphs regularly. Work through real-world problems and always remember to consider whether direction matters in your calculations. Speed and velocity are fundamental concepts that bridge basic physics with advanced applications. Master these foundations, and you'll be well prepared for more complex physics topics ahead.